Here we're going to take some examples on trajectory generation. Our first example is generate a linear trajectory equation to travel from t initial to t final in 5 seconds, where t initial is given here and t final is given here. So we're given t initial, t final, and the total time required to go from t initial to t final. Let's look at the solution. So since the time is given here, we're given time, that means inherently we need to find a continuous Cartesian trajectory. So we're looking at a trajectory equation rather than via points. Now I want you to notice here that t initial and t final include the same rotation matrix. So the rotation portion here is the same as the rotation portion here. This means that our trajectory will not have any change in orientation. So only translation portion will be changed, and that's where we find the trajectory equations for translation portion. All right, so the first step is to find the velocities for the Cartesian coordinates. So the velocity for x will be x dot equals to x final minus x initial. So this will be my x final, 10, minus x initial, which is 2, divided by the total time, which is 5, that's given here. And that equals to 1.6 units per second. Okay, so that's my velocity in the x direction. And then my Cartesian velocity in the y direction, again, y final minus y initial. Y final is here, -2. Y initial is here, 6. So -2 minus 6 divided by the total time, which is 5. And that would give me -1.6 units per second. Now for my third Cartesian coordinate, z, I can find the velocity along the z direction. In this case, z dot equals to z final minus z initial. My z final here is 15 and z initial is 10. So I substitute them here. And then that's divided by the total time, which is 5 seconds. So that gives me 1 unit per second for this velocity. Now I'm ready to put together the trajectory equation for x, y, and z coordinates. The linear equation for the x is x initial, which is 2 from right here, plus 1.6, which is x dot from right here, times t, which is the time that we can substitute for any time that we require to find the x. Similarly for the y, equals to y initial, which is 6 from here, minus x or y dot, which was what we found here, -1.6, multiplied by t. And then for the z coordinate, z equals to z initial, which we have right here, plus z dot, which we have found here to be 1, multiplied by t. So these are my 3 equations that represent the trajectory in my 3 Cartesian linear coordinates. Now if I would like to put this in a matrix form, matrix trajectory form, since I have the orientation here the same, it didn't change from the initial to the final. Okay, so I can leave this the way it is as the orientation, and then in the x, y, z I can just replace them by the equation for each one of the x, y, and z. So I take them from here and I put them in my transformation matrix for 4th column. Okay, so that gives me the trajectory for the Cartesian space of the end-effector. Let's take another example. Example 2. Generate a Cartesian trajectory to travel from t initial to t final in 5 steps. And you notice here we're given the number of steps, not the time. So that means here that we need to find a discrete trajectory, not a continuous trajectory. And we're given t initial and t final. Okay, and I want you to notice here that the rotation portion of the t initial and t final are different. So in this case, we're going to have to find discrete trajectories for the orientation portion of the Cartesian coordinates. All right. So let's start our solution here. Since we are given number of steps, that means we need to generate a discrete trajectory. Okay. So we're going to start first with the linear motion, the xyz trajectories. Okay. So for the linear coordinates xyz, we can find the steps as follows. For x step equals to x final minus x initial, which are given here. X final is 10 minus x initial is 2. So 10 minus 2 divided by the number of steps, which are 5 steps. So that gives me 1.6 units for each step in the x direction. For the y direction, I can find y step. Again, y final minus y initial. Y final in this case was -2 and y initial was 6. So that's -2 minus 6 divided by the number of steps, which is 5. And that gives me -1.6 units in the y direction. Now in the z direction, the z step equals to z final minus z initial. Z final here is 15 and z initial is 10, and that's divided by the number of steps, which is 5, and that gives me 1 unit in the z direction. Now I can go ahead and construct the trajectories for each one of the coordinates. For the x coordinates, I'm going to start here with the x initial, which is right here. Okay, so that's x initial. And then here I have x initial plus 1 extra step. So I'm adding x initial to 1.6, and that gives me 3.6. And then the next step would be x initial plus 2x steps. That would be 5.2. And then x initial plus 3x steps. That would be 6.8. And then initial plus 4x steps, and that would be 8.4. And then that would lead me to the final x, which is 10. Okay, we can do the same thing for the y. Again, I start with y initial, which is 6, and then the next step would be y initial plus 1 step. Okay, and then I keep going on until I reach my y final. And then the same thing for the z coordinate trajectory. I start with z initial, which is 10, and then I add to this 1 z step at each step until I reach my final z, which is 15 in this case. For the Cartesian orientation coordinates, the rotation matrix from initial to final will have to be defined. Remember, this method here is a different method from finding the Cartesian linear coordinates, x, y, z. So here, this is a long method that we discussed earlier. The initial to final orientation rotation matrix would be defined as R initial transpose times R final, both of which are given. So this is the transpose of R initial, and this is the R final. Both of them are taken from T initial and T final. And upon multiplying these two rotation matrices, I can find the rotation matrix between the two rotation matrices here. Now I'm ready to find the single angle representation of R. I put here the general equation form. So I need to find A tan 2 of R32 minus R23. R32 is this one here, minus R23, that's 1, 2, that's right here. So if I put these together and square them, that would be the first element here. And then the second element is R13 minus R31 square. Again, we can find it from this rotation matrix. And then the third element is R21 minus R12 square, which we can find again from here. And then the second argument for this function is R11 plus R22 plus R33, which is the diagonal elements of this rotation matrix, minus 1. So when I evaluate this, all these numbers are substituted here. When I evaluate this, I can find the single angle representation of the rotation, which is phi equals to 0.7632 radians. And I can convert radians to degrees, which would be 43.73 degrees. Okay, now I'm ready to find sine phi and cosine phi and v phi. So sine phi, I'm just substituting the phi that we found here, which equals this number, and then cosine phi equals this number, and then v phi is 1 minus cosine phi, which is this number. Now, since I already have the phi angle, I can look at which category. Remember, we have different cases or conditions for finding the single axis. So in this case, since phi is between 0 and 90 degrees, this is the condition for phi between 0 and 90 degrees. That means we can define k as follows. So k is kx, ky, kz, which equals to these expressions 1 over 2 sine phi, and then the differences in some elements of the r from here. So we can directly substitute these values, which we already have. We already have the sine phi which is this particular value. And then I have R32 minus R23 here, and then this difference here and this difference here. If we evaluate this, we're going to come up with this final k vector. Okay. And then we're ready to find the step angle for the trajectory. So if we have phi total and we have the number of steps, in this case it was 5, then phi step equals to the total phi divided by the number of steps. So if we do that division, then we have the step angle as 0.1526 radians. Now I can go ahead and find the trajectory delta angles for this rotation. And I'm going to start here with 0. That's 0 between the difference between the initial and final transformation, 0. And then this is 1 step angle, 2 step angles, 3 step angles, 4 step angles, and 5 step angles will take me to the full angle that I have here for phi. Okay, so that gives me here the trajectory delta angles that I will need for the next step. In the next step here, we need to convert these trajectory delta angles that we found in the previous slide back into delta rotation matrices. Okay, so the delta angles have to be converted back into delta rotation matrices. This is the general form of the delta rotation matrix. Again, kx, ky, kz are constants that we found in the previous slide. And then cosine phi, sine phi, and v phi are going to be different for each trajectory point. Okay, so now since we have the phis for each trajectory point, we can go ahead and substitute here for each point, and the results will be as shown here. So delta R1, so we substituted basically the first theta or phi trajectory point in here, and we got delta R1. As you can see, the first one is identity matrix. Okay, and then when we substitute the second step from the phi, that would give us this dr2, and then the third step would be dr3. Each one of these steps were substituting the phi from the trajectory of angle deltas that we found earlier in the previous slide, and then we keep going until we found the last delta r6 using the last phi, which is the full phi that we found in the single angle representation. Okay, so this will be the trajectory delta rotations that we're going to be using to find the trajectory of the orientations for the Cartesian end-effector. For the next step, we need to pre-multiply each of the delta rotation matrices that we found in the previous slide by the initial rotation matrix that was given in the example. Okay, so these would be the rotation matrices that would be required for my orientation trajectory. So our trajectory, these are the trajectory rotation matrices that we need for going from the initial to the final transformation matrix. And the first step here would be R initial times delta R1. The next step would be R initial times delta R2. The next step will be R initial times delta R3. And then R initial times delta R4, R initial times delta R5, and then R initial delta times delta R6. This final rotation here would be identical to the rotation matrix of the final step in the transformation matrix that was given in the example. Okay, so if we do these multiplications here, we're going to look and find these rotation matrices. This is the first rotation matrix, which is identical to the initial rotation matrix that we can extract from transformation T initial. And if you guys recall in the previous slide, delta R1 was identity matrix. So if that's multiplied by R initial, naturally we're going to get R initial as it is right here. And then this is my first step, and then second step orientation, third step, fourth step, and my fifth step orientation is right here. So this orientation here, rotation matrix, is equivalent or the same as R final that was given in T final in the example. Okay, so basically this ends my trajectory for rotation. If you recall a few slides ago, I also found my trajectory for the translation, the XYZ translation. So now that we have both the linear and angular coordinates trajectories, we can combine them together to find the trajectory transformation matrices. Okay, so we're going to take the orientation portion, the rotation matrices from here, and we're going to take the translation portion from the few slides that where we found x and y and z trajectories. Okay, so t trajectory now equals to, and this is our first point, which is identical to t initial. And then we go to our first step, and then second step, and third step, and fourth step, and then fifth step. And that fifth step would be identical to t final that was given in the example. Let's take an example here on joint trajectories in the joint domain. Example 3, generate linear joint trajectories for a RRP robot to travel from Q initial to Q final in 5 steps, where Q initial is given here and Q final is given right here. Now I want you to notice here that this robot is an RRP robot. That means revolute, and prismatic joint. So the revolute joints have angles in degrees, and then the prismatic joint have distance in units of distance. Okay, so the first values here, the first values in the Q initial and Q final have units of degrees because they are revolute joints, and then the second values in the Q initial and Q final are also in degrees because they are for revolute joint angles, and then the third values in Q initial and Q final are prismatic joints, so these are distances and in unit distance because it's a prismatic joint. Now, since we are given the number of steps here, 5 steps, that means we are required to find a discrete trajectory with via points. Okay, now to start with the discrete trajectory, let's find the steps for each one of the joints. I'm going to start here with theta 1 step for the first joint, which is theta 1 final minus theta 1 initial. Theta 1 final is given here as 100, and theta 1 initial is given as 45. And then we divide this by the number of steps, which is 5, that's given in the example. So that gives me 11 degrees for the step of theta 1. Now theta 2 step, similar way, we can start with theta 2 final minus theta 2 initial. Both of them are given. This is theta 2 final and theta 2 initial. And divide this by the number of steps, which is 5. And that gives me negative 2.5 degrees for theta 2 step. Now for the third joint, we have D3. The variable for the prismatic joint is D. So the step for D3 is D3 final minus D3 initial. D3 final is given here as 70, and D3 initial is given here as 210. And we divide this by the number of steps, 5, which would give me negative 28 units. So now we are ready to construct the trajectories for each one of these joints. Starting with theta 1, I'm going to start with theta 1 initial, which is 45, as we see here. And then the second step would be theta 1 initial plus theta 1 step. So 45 plus 11, that gives me 56. And then the next step would be theta 1 initial plus 2 steps. And then we keep going all the way until we find or we reach theta 1 final, which is 100, that was given here in the Q final. We can do the same thing for theta 2. We start with theta 2 initial, which was given right here, and then theta 2 initial plus theta 2 step, which is negative 2.5 degrees. So that would give me 19.5. And then we keep going all the way until we reach theta 2 final, which is 9.5 degrees. And that was given here in the Q final as well. Now we move to the third joint, which is D3. And that joint variable can start with D3 initial, which is 210, that was given in Q initial. And then the next step would be D3 initial plus D3 step, which is negative 28 units. So that would give me the second step. And then we keep going until we reach D3 final, which was given here as 70 in the Q final. And that will give me the trajectory for D3. So these are my 3 trajectories for each one of the joints. I can leave them this way, or I can reconstruct them back into vectors in a similar fashion as it was given here, Qi and Q final. So I can assemble them as Q trajectory. The first vector would be identical to Q initial. And then the second vector would be q initial plus q step for each one of these three. And then we keep going all the way until we reach q final, which would be identical to q final that was given in the example. Let's take another example on joint trajectories in the joint domain. Example 4, generate linear joint trajectories for a RRP robot to travel from q initial to q final in 5 seconds, where q initial is given here and q final is given right here. Now, if you look here, we are given the total time in 5 seconds as opposed to number of steps. That means we need to find trajectory equations instead of trajectory via points. Okay, again, we're using here RRP robot. That means revolute and prismatic joints. Okay, so the first value here is a joint angle in degrees. Second value is joint angle in degrees for the second revolute joint. And the third value is in unit distance because it's a prismatic joint, and these are in unit distance for the prismatic joint. Now we can start this here by finding the joint velocities for each one of the joints. I'm going to start with theta 1 dot for the first joint, which equals to theta 1 final minus theta 1 initial. Theta 1 final is given as 100, and theta 1 initial is given as 45. I divide this by the total time, which is 5 seconds, and that would give me 11 degrees per second for the velocity of the first joint. For the velocity of the second joint, theta 2 dot equals to theta 2 final minus theta 2 initial. Again, both of them are given here. This is theta 2 final and theta 2 initial. And I divide this by the total time, which is 5 seconds. And that would give me negative 2.5 degrees per second. For the third joint, I can find d3 dot. Again, remember the variable for the prismatic joint is d. So d3 dot is d3 final minus d3 initial. d3 final is 70 and d3 initial is 210. And I divide this by the total time, which is 5 seconds. And that would give me negative 28 units per second. Now I'm ready to construct the trajectory equations for each one of these variables. So starting with theta 1 equation equals to theta 1 initial, which was here 45, plus theta 1 dot, which we just found as 11 degrees per second, times t. So theta 1 equals to 45 plus 11 t. For the second variable, theta 2, again, theta 2 equals to theta 2 initial, which was given here, 22, minus theta 2 dot, which is negative 25, and then this is multiplied by t. So the equation for the trajectory of joint 2 would be 22 minus 2.5 t. For the third variable, d3 equals to d3 initial, which is given as 210, minus 28, which is what we have for d3 dot, times t. So the equation for the trajectory of d3 would be 210 minus 28 t. Now we can leave them this way, or we can just add them to a vector that would be similar fashion to what we have here for q initial and q final. So we can call this q trajectory, which equals to, and then we put the equation for each one of these variables in its respective space here. So this would be the trajectory for joint 1, theta 1 I mean, and this is the equation for trajectory for theta 2, and this is the equation for the trajectory for d3.